So an important point about differential equations is that, except for a few special cases, you won't be able to find nice formulas that describe the solutions. Luckily, a lot of these special cases do come up in real-life problems, and we will be studying those later. But it's important to have something to fall back on if you can't actually solve the equation. And that fallback is to find approximate numerical solutions. Now, there are different ways to do this, but in this class, because this is an introduction to the subject, we're going to teach you the most basic technique, which is called Euler's method. So first, I'll give you the intuitive idea behind Euler's method, and then I'll describe the process in more detail. So suppose you had a differential equation where the slope field looks like this, and you want to find a solution with some initial value. Let's say that y of 0 is equal to 2. So the idea behind Euler's method is that you would first find the point where x is equal to 0 and y is equal to 2 on the graph, and you would look at the slope at that point. And then you would follow that slope in a straight line until you reach a certain x value. And then you would look at the slope at that point and follow it in a straight line. And look at the slope at that point and follow it in a straight line. And then you keep going until you've sketched out this approximate curve far enough to answer the question that you're trying to answer. And so you can see from the picture that you do actually get something that looks sort of like a curve that's a solution to the equation. It's not actually a solution. It's kind of boxy instead of being curvy, but you do actually get a pretty good approximation this way, and you can get better and better approximations by making the steps that you take, like how far you go in those straight lines, by making that smaller and smaller. All right, so let's get into the details. How does Euler's method actually work? So the first thing you need to do is you need to choose a specific step size, delta x. This measures how far you go at each step of the process. And this is something where if we give you a problem, we'll probably tell you what step size to use, but in a real-life situation, you would get to choose that step size. And there's a trade-off there. If you use a larger step size, then the amount of computation you'll have to do to get an answer is less. Whereas if you use a smaller step size, then you're going to get a more accurate approximation of the solution. But anyway, once you've chosen the step size, then the rest of the process is quite systematic. So what happens next is you use the initial value that you're given as part of the problem. You use that initial value to compute dy dx using the differential equation. Then you would use that dy dx to compute your delta y, using the formula that delta y is dy dx times delta x. And now you have a change in x and a change in y, and you can use that to get a new point. So the new point has coordinates x plus delta x and y plus delta y. So now at this point you've moved one step from the initial point, and you can repeat using this new point as the initial point. So what that means is that you return to step 2 using this new point in place of the initial point. So some of you might have some computer programming experience, and if you do, you could look at this set of instructions here, and you could see that this really is just a systematic process that you could program into a computer with a few lines of code. And in practice, that is what happens. You would use the computers to do Euler's method for you. In this class, we're going to have you do a few steps of Euler's method by hand, but the reason is that we want to make sure that you understand how the algorithm works. Okay, so here's an example. Suppose y of x satisfies this differential equation. dy dx equals 0.03y plus 1000, with initial value y of 0 is equal to 0. Use Euler's method with delta x equals 1 to estimate y of 3. And just as a side note, this differential equation could be used to model a bank account where you're earning 3% interest and putting in $1,000 per year into the account. And so this question would be to estimate how much money you would have in the account after 3 years. And it might actually help as we go through Euler's method to think about this, because the difference between what we'll do with Euler's method and the differential equation is that the differential equation is supposed to be a continuous process, where in this situation with the bank account, you would be continually earning interest and continually depositing money into the account. Whereas with Euler's method, we turn it into a discrete process where at the end of every year, you make the deposit and then you earn interest. And then you go to the next year, make the deposit, earn interest. So when we do Euler's method, we're using that discrete process to approximate the continuous process. So anyway, here's how it works. It can help to make a little table where you have these 5 columns. Because the initial value that's given is y of 0 is equal to 0, the first entries that we put in this table are x equals 0 and y equals 0. And there are some other entries in this table that we could go ahead and fill out with basically no calculation. So first of all, we're given as part of the problem that delta x should be equal to 1. So we could just fill out that whole column with 1s. And in fact, if you wanted to, you could even skip that column because it doesn't give you any information that you didn't already know. But then once we know what delta x is, we could go ahead and fill out the x values on the table. Delta x being equal to 1 means that the x values increase by 1 in each step. So the x values will be 1, 2, 3, and then we can stop at 3 because we know that the problem is asking us to find y of 3. Okay, but now the rest of the table needs to be filled out in a systematic way. For this first dy dx entry, we would use the differential equation and plug in the x and y values to get dy dx. In this case, the differential equation only depends on y and not on x, and so we would just plug in the y value. And so when we plug in y equals 0, we would get dy dx is equal to 1,000. And now we can use that to calculate delta y using the formula that delta y is equal to dy dx times delta x. So in this case, that's 1,000. And now we can calculate the next entry in the y column using the rule that the new y should be the old y plus delta y. And then we would use that y value to calculate the dy dx in that row. So when we plug in y equals 1,000 into the formula for dy dx, then we get dy dx is 1,030. And so then delta y is again dy dx times delta x, and so we get 1,030 for delta y. And then the new y is the old y plus delta y, and so that's 2,030. And then when we plug in y equals 2,030 into the formula for dy dx, we get 1,060.9. You probably should double check that calculation for yourself, but that's what it is. And so then our delta y is dy dx times delta x, and the new y value is going to be 3,090.9. And we can stop now because that is the estimate for the y value when x is equal to 3. So 3090.9 is the answer. If it feels like we were just filling out an Excel spreadsheet by hand, that's because we kind of were. And if you like Excel, it's a pretty good way to do calculations with smaller values of delta x where you have to have a lot more rows. So for example, if you use delta x is equal to 0.1, then your x would increase by 0.1 at each step, and you'd have to do 30 rows worth of calculations. But if you do it using Excel or a computer program, then you would get that y of 3 is approximately 3134.2. So that's a little bit different from the answer that we got using delta x equals 1. Well, it turns out that this differential equation can be solved exactly, and you'll actually learn how to solve equations like this in the next class. Well, if you do that, the exact value of y of 3 ends up being about 3139.1. So you can see that when we used delta x equals 1, we got a decent estimate, but it wasn't super close. When we used delta x equals 0.1, we got a much better estimate. And you get better and better estimates as you use smaller and smaller values of delta x. So the general rule for that is that the error with Euler's method is proportional to the step size, this delta x. And so what that means is that if you cut the step size by a factor of 10, then that should also cut the error by a factor of 10, roughly. So that's something to keep in mind when you're choosing your step sizes. All right, that's everything you need to know right now. See ya.